Right. Good afternoon, everyone. Take your seats. So, last week we completed up to which part? What is the area that we covered last? We did ketones. Yes. Sorry. We moved on to how alcohols react with carboxylic acids and how ketones are also produced. Right. So, before we move on to anything else, I would like to see whether you can remember some past conversions we have learned about. So, shall we start with two questions? Okay. So, we have learned about alkyl halides, we have learned about different types of other reactions. We have now learned about alcohols as well. So, alcohol all the way up to acidification is completed. So, let's start with a simple question. And let's see whether we can build on that question. So I would like to start with this part. Now this is somewhat related to, I would say, alkyl halides, and then your knowledge about the reactions of alkyl halides, because we need to always keep reminding ourselves of things that we have studied in the past. So now write down this conversion. This is something that I wanted to do in the beginning of the class today. How do you convert this into this? We'll start with that simple thing. You all have your exams these days, right? Are you done with yours, Pisati? Can I see the last thing that we did? We do SN1, SN2? SN1, SN2? Right. Acidification. Right. Organic compounds. Right. Alkyl halide SN1, SN2 is done. Good. So this is a trick that you should memorize going forward, okay? This particular reaction is something you should remember. Is there anyone who's done? Done? Very good. Let's see. Okay, you put HBr. Okay, and then you did that. Okay, so now I'm not saying this is entirely wrong, but when you put HBr, where does the Br go? Where does the hydrogen go? Will go to the place where there's more hydrogen. Okay, bromine, less hydrogen. Okay, if that is correct, no problem. I'm not saying it's wrong. I just wanted you to know whether you have done it like with a proper understanding. Okay. Right. So, students, let's see. Now there was this one student who did it. So, let's say we put HBr. Right. We put HBr. Then what happens? We have HBr added across the double bond, right? So across the double bond, hydrogen goes to the place where there is more hydrogen. Here, correct. And bromine goes to the place where there is less hydrogen. Correct, right? So this is the product you get. But after that, you need to again remove the bromine to get to that product. So let's say you put ethanolic, sodium hydroxide, or KOH, either one is fine. So then when you're removing hydrogen and Br, yes, this Br will go with a hydrogen from an adjacent carbon atom. So in the nearby carbon atoms, hydrogen will be taken along with this Br, right? We learned about it under alkyl halides. So obviously Br is leaving, hydrogen here or hydrogen here should be leaving along with it. So we take hydrogen from the carbon where there is less hydrogen. Is that clear? So this carbon has how many hydrogens now? 3 hydrogens. This carbon has how many hydrogens now? 2 hydrogens. So we are taking hydrogens from which carbon? This carbon. Is that clear? So therefore, when a hydrogen from here and Br here is removed, you form a double bond here. Is that clear? So then we get this product. Very good, right? Very good. So if you have gotten to that answer, very good. So I need to do one more question. Actually, we are going to do a few more questions today. Okay? Done? Now I don't have to write it, but can you do the opposite of this conversion? We have the double bond there, and I want the double bond to be here, opposite. Can you try? Bear with me, students. Sorry. No need to do opposite. It's going to be quite easy. I'm sorry. The opposite of this is also going to be super simple. So, for example, if you have what do you call it? If you had HBr here, hydrogen will go here, Br will go here, either one is fine. And then what happens is there's a Br here. You can actually try to get the hydrogen over here to leave, but actually doing that will have more than one step. You have to do it in a much more lengthy process, not necessarily easily done like this one. So we'll leave that question for the time being. We want to move on to another small question that I will give you using alkyl halides and alcohols, because we learned about alkyl halides and alcohols, how we convert alkyl halides into alcohols as well. So first of all, copy this down and finish it off. I'll give you another question. Are we done copying this down? Do this conversion, please. Please do this one. පල්ලෙන් ගලවන් ඇවිල්ලා ගහමද මේක මෙතන? මොකද මං පල්ලෙහාකට කනෙක්ට් වෙලා තිබ්බේ. අවුලක් නෑ හැබැයි. දෙවක ඕන කෙටින්. Ready? Thank you. Anyone who is done with this? HBR, BR. Now, you are not wrong. You can get a BR and then BR can be converted to OH. But the position of the BR here and the OH is not matching, no? You have to think about that. Here I have seen all of you doing the... Are you done? H2SO4. Here also, now when it comes to H2SO4 addition is done to do what? Add a water molecule across the double bond. Hydrogen goes to one place, OH goes to another. Same story. Hydrogen goes to the place where there's more hydrogen. OH goes to the place where there's less hydrogen. So has it happened like that? No, OH has gone to the place where there's more hydrogen, no? Is that clear? So one step conversion is not possible here. Come in. Are you new with this? Right, take a seat. Today we are doing some organic conversions. Have you done organic chemistry? What about this now? So I have seen most of you have done HBr addition. Fine. Right, HBr. And you are getting to something like this, CH3, CH2. So hydrogen goes to the place where there's more hydrogen, so hydrogen is here. Bromine goes to the place where there's less hydrogen, like so. And then I have seen most of you have done aqueous sodium hydroxide addition, right? Aqueous sodium hydroxide, we have added aqueous sodium hydroxide to this. right? So then Br group will turn into OH group, which is also true. Then what is the problem here? Br is here, so the OH should come into the middle carbon, not into a corner carbon like that. So how do we fix this? We add HBr in the presence of what? An organic peroxide. So something like this would do. Then what happens? Can you remember Markovnikov's addition and anti-Markovnikov's addition? Right? Anti-Markovnikov's addition happens. That means hydrogen goes to the place where there is less hydrogen, and bromine goes to the place where there is more hydrogen. Is that clear? It goes in the opposite way. Then you can add sodium hydroxide, aqueous medium sodium hydroxide. Then at that point, what you produce is the product that we want to produce. Is that understood? So these are basic tricks, students, that we usually use, something that you need to keep in mind. Try your best to remember these two reactions. See, the past ones you should remember, right? Otherwise it will be a problem. So I'm double checking whether you guys remember these things. Okay? Can I erase this? Right, let's see if you remember this. Same starting compound. There are a few ways you can do this. Right? I want you to show me the at least two methods. Now, I know you would do it in one method easily. I want you to show me another method, like use of, I will give you a little bit of a hint. You need to use Hg2+. That's a little bit of a hint. Using that, can you please do that conversion, please? Hg2+ should be used. There are other methods. That's why I specify Hg2+ must be used. Otherwise, you will use an easier method. In the sense, method that you remember, rather than the one that I want you to do. There are two methods we can use. But the second method you haven't learned yet. You only know one method at this point. That also you're not sure, no? The one method you know. See, the further back I go in the theory parts, the more clueless you guys look. These are from old theory parts. We are done. Do you remember any reaction that uses Hg2+? Can't remember? So, can you remember alkyne reactions? Turn to alkyne reactions and see if you find any Hg2+ reactions there. Any Hg2 plus reactions there? You found it. Alkynes. Do we have Hg2 plus? Yes, no? So let me help you here. So students, we can produce this. I'll tell you up to this point, right? We can produce this if you have a alkyne group, right? Meaning something like this. Now there's an addition of water reaction that can take place in the presence of Hg2 plus. So we write usually Hg2 plus and H plus H2O, or else you can just write dilute sulfuric acid, Hg2 plus and dilute sulfuric acid, if that is also fine. Like if you have written Hg2 plus dilute sulfuric, that is also fine, right? Because there is H plus as well as water in dilute sulfuric. So anyway, so if you add this, initially what happens is, students, there will be a water molecule added here. H plus goes here, OH minus, hydrogen goes here, OH minus comes to this carbon. What is formed is called enol, which is unstable. I have given you these notes, right? So they get rearranged to form a keto group, right? If the OH is in the middle, then there will be a ketone produced. If the OH happens to be in a corner, it will be forming aldehyde, right? So this produces our final product. So now you have to find out a way to get to that point. So that's up to you. Find out a way to get to that point at least. How do you get there? We will add something here. What is it that we can add? We can add Br2 in CCl4, right? We usually write Br2. We can write Br2 in carbon tetrachloride, because usually if you take Br2, we have it in an organic solvent, right? When it comes to aqueous medium Br2, there can be further reactions taking place. So therefore, we like to write Br2 CCl4. So then what you produce is this. There is a hydrogen here, and this carbon will get a bromine, as well as other carbon will also get a bromine, right? This carbon has 2 hydrogens. Each bromine here, let's say this bromine, will leave with the adjacent carbon's hydrogen. Adjacent carbon happens to be this one, so therefore there will be hydrogen going with this bromine. And what happens? There will be a double bond formed here, right? And this bromine will leave with the adjacent carbon hydrogen. So adjacent carbon could be this one or this one. Adjacent means nearby carbon. So nearby carbon's hydrogen. This carbon has 3 hydrogens, this carbon has only 2 hydrogens. So it takes from the place where there is less hydrogen. Always. Whenever you are removing hydrogen, we always remove hydrogens from the place where there is already less hydrogen. Right? We take from the poor, give to the rich. Is that clear? So this is the hydrogen that leaves. So as these hydrogen and Br leaves, another bond will be introduced into the middle. Right? So when these guys leave together, one bond additionally is formed. When these two leave together, another additional bond is formed. Is that clear? Altogether, a triple bond is formed. So what is the reagent that we add? Elimination reactions of alkyl halides. What do we add? NaOH or KOH in ethanolic medium, or alcohol medium. Is that clear? So this is something to keep in mind, students. This is something to keep in mind. Very, very important. Is that clear? So take this down. I feel like testing you with another one. I'll give you one more question, okay? Because this is bad. Like if you can't remember things that we have learned in the past, it's bad, because I'm going to be having, now by next week everyone is done with all the additional work, right? You don't have any exams or anything like that, no? Because next week I will have one whole day class where we are going to allocate the first few hours for the theory, the last few hours when you are a little bit tired, I'll be having the entire last 4 hours conversions only. So I want you to be prepared for a class like that next week, because I've been wanting to have a class. Last week also you guys said this week we can't, right? So we will be having it next week. Okay, right, let's do a good one now. Difficult one, right? In the sense of multiple step one, right? Write down a question. You have to write a sentence here. Write down a question. Using the given reactant, as the only organic compound, show how the following conversion can be done. Show how the following conversion can be done. Okay, let's see. So this is the only organic compound that is given. You can't bring additional organic compounds right in the middle. Okay, that is not possible. So what I want you to do is this. So you need to do this. You can't bring any other organic compounds in the middle. Right? I will help you a little bit here. This reaction happens. Now, normally you don't get help like that. You need to observe it on your own. This reaction happens through alkyl halides. This reaction happens through alkyl halides. Right? Can you remember? You can. The first thing to do is quickly jump into the there's a summary of alkyl halides I gave you, right? Look into that, and then you can figure out what two components are there in this final product. You will see the two parts. Okay, I need to get to these two parts. Then only I will produce this. So then focus on producing those two molecules. There are two molecules that are joining together to form this. Now I'm helping you out a lot here because it's the first time you are doing this, right? So I need you to develop a little bit of an understanding of how this is done. So if you take a look at alkyl halide reactions, you will see there are two molecules that are joined together here. So you try to figure out what the molecules are, and from there onwards your focus is to how to produce both the different molecules starting from only this. Is that clear? So first try to take a look at that. Did you identify the reaction here? Which one? Okay, good. Alkyl halide parts. Was planning on finishing off alcohols as soon as I came, but I thought since you all are still thinking of how to do simple conversions, we'll do a few conversions. Did you understand the two sections that you need to form? Very good. You are making good progress there. Now, something that we did today is going to be used here. A part of a conversion we did today is used here. I will start the discussion in a minute, okay? I'll give you some more time. Minute or 2 minutes. Done? Okay, very good, very good. Have you finished this at school?
We did this last week.
We? Us? Same thing?
Yeah.
Yeah. Like this part. And then two connecting together, it's a bit of a different one, no? Right. So this one was HBR addition and all that. My God, friends, we have done a very almost 99% similar question, right? So you should be getting to answers really fast then. We have done, when was this? Last week? Only difference was the alkyl halide addition section, right? Earlier the BR was here in the previous question. In this question the BR is here, right? So if that is the case, you should be getting to answers a bit faster, right? So students, you have to identify the fact that this happened through these two molecules joining together. You need to remember alkyl halides, when reacted with acetylide ions, usually form connected molecules like this. We'll say we had Br here, right? We are more familiar with Br being present, and this section is C triple bond and CH3, and this side is negative. There's a lone pair on carbon. So this is a nucleophile. Nucleophiles and alkyl halides react. Basically what happens is this nucleophile electrons are going to be donated here, and this bond will be broken, and these two things will be joined together. Right? Alkyl halide reactions. Alkyl halides react with nucleophiles a lot. Right? OR groups, ammonia, water. Right? Alkyl halides react a lot with these things. You should remember these. So producing this is super easy. You can easily produce this in a single step. You just have to add HBr. That's it. Then what happens? Hydrogen goes here, bromine goes here. So although I have drawn the molecule bent like this, it's the same as writing Br here and hydrogen here. Right? I have drawn the molecule bent because the final molecule I have written it in such a way that you can easily identify the longest carbon chain. So if you wrote it in a straight chain form, the bromine is still going to be on the second carbon like we have here. So when you add HBr here, hydrogen goes to this, bromine goes to this, which is the same thing as what I have written there. That's the first molecule. And the second molecule can be produced by adding Br2. If you add Br2 CCl4, in CCl4, you will get something like CH3, CH, CH2, and on both sides we will have Br and Br. And we little while ago did the formation of a triple bond, so we can add ethanolic sodium hydroxide or KOH. So at that point you will produce this CH3, C triple bond C, and this is an alkyne with a terminal hydrogen. So when you have terminal hydrogen, if you react it with sodium, you produce this, right? So this is an ionic compound, right? This is the acetylide ion, this is the sodium ion. So whenever we react this and this together, the negatively charged acetylide ion will react with the alkyl halide and will produce the product that we want. Is that clear? So I would say the question that we have done is 99% similar to this. So you should be able to remember this question pattern, students. It's like this. When you are doing organic chemistry, the more you remember the basic equations and the common ones we use, the easier it will be. You start seeing things, right? For example, I told you this before also. If I ask you, now imagine you are not calculators, no? Right? But if I ask you, what number should be taken to the square root to produce 1.414? 1.414 is square root of 2. Now, did anyone ask you to remember that? No. But your brains remember it, right? Why? Because you have been doing it so many times in physics. Not in chemistry, of course. In physics, you do this a lot, right? Square root of 2, square root of 3. I can't remember 3 now. It's like when I was this thing, I remember, now I can't. What is the square root of 3? 1 point? Sorry? 1.7? 1. Okay, I can't remember. Right? So there must be something like that, right? So you should be, now you see these numbers and it means something to you. When you see it, you know how to get to that number by taking square root of 2. Right? So just like that, when you see these kind of conversions, you see the connections. Like, it's something you start seeing. This section could be added to this if this part was alkyl halide. Right? This entire part can be added to this through alkyl halide. You will start seeing it that way. Right? That vision will be only developed if you have actually studied these parts and have a good memory bank of the reactions and the mechanisms that we have learned. And apart from that, we will be doing questions also to improve your skill to get to the answers. Okay, so we have to do. That's why I'm saying, like, if I can take one whole day and do questions with you, I will do it. Right? So we will do one. So then you will be in a better form at the end of the day. Okay, so try your best to remember these things. So we'll finish alcohols and aldehydes and ketones today somehow, and we will get to more questions after that, right? So take this down. I want to finish alcohol section and aldehyde section, so we will quickly do that, and then we'll move on. When how do you like the new arrangement? Is it better? That arrangement better than this? Okay, good. Right. Okay. Take a new heading after this. Take a new heading after this. So now we were talking about alcohols. I think I discussed two reactions with alcohols, right? Under those we discussed the breaking of oxygen hydrogen bonds of alcohols. Now that part is done. Now take a new heading. Breaking of carbon oxygen bond of alcohols, or cleavage of carbon oxygen bonds of alcohols, right? So we are planning on cleaving this carbon oxygen bond. The bond breaking. First point under that. These reactions take place through nucleophilic substitution mechanisms. I'll give you the basic reactions and I want you to take this down. Right, so there are a few other reactions. I will write everything down, otherwise. Bear with me a second, students. I can't write all the reactions if I write CH3 here. But okay, first of all, take this part down and leave some space onto this side. Okay, leave some space onto this side. Right. So students, when it comes to Lucas reagent, one thing to keep in mind is you can use zinc or zinc chloride, but even if you add zinc in the presence of HCl, it will turn into zinc chloride, right? Because zinc can easily react with HCl and will produce zinc chloride. Either one is fine, but since we don't want to decrease the concentration of HCl a lot due to the reaction of zinc metal, we sometimes directly add zinc chloride like this. So this is called Lucas reagent. I will give you a note on this separately because this is a bit of an important theory part. I'll give you a note on that separately, okay? Take it down for the time being. I will give you a note under this. Okay, are we done? Right. So here students, what happens here is, if you add to alcohol concentrated HBr, this group will be substituted with a Br group, right? So directly form like alkyl halide without any issue. This concentration, concentrated hydrogen halide addition. This is a hydrogen halide, right? So when you have a concentrated hydrogen halide like HBr or HI, nicely this OH group will be turned into this, no problem. But unfortunately, when it comes to concentrated HCl, we can't do this. If it was, it would have been easier for you to remember everything, right? So concentrated HBr, HI, HCl, everyone produces alkyl halide with alcohol. No, when it comes to HCl, that doesn't happen. For HCl, you need to have someone who can accept a lone pair of electrons, right? So anything that can accept a lone pair of electrons is referred to as a Lewis what? Acid or a base, students? Anything that can accept a lone pair of electrons is referred to as a Lewis acid or Lewis base. Lewis. Now, we actually, students, learn that there are two main categories of acids and bases. One is Lewis acids, the other one is Lewis bases. Now, what do you know about acid? Normal acid, it is capable of releasing H+. Right, so Lewis acids are also acids that are capable of donating a H+. Donating H+ is usually, like, referred to as donation of a proton. H+ is a proton, right? Lewis acids are capable of donating a proton. Or we say accepting a lone pair. Donating a proton or accepting a lone pair. These are two things that Lewis acid does. A Lewis base can do the exact opposite of what Lewis acids do. Lewis acids donates a proton and accepts a lone pair. When it comes to Lewis bases, they can donate a lone pair or accept a proton. Is that clear? Vice versa, right? So this zinc 2 plus is capable of accepting a lone pair, so therefore this is acting as a Lewis acid. So normally this HCl, when you are reacting HCl with alcohol, for it to work, you need to have a Lewis acid, right? You need to have a Lewis acid. Is that clear? So this particular mixture of things, concentrated HCl and zinc chloride together, is referred to as a Lucas reagent. Lucas reagent is actually used to identify, I will write used, primary, secondary and tertiary alcohols. Okay, so I will fill in the details here. The alkyl halides are usually water insoluble. They are not very soluble in water. Small alkyl halides like this is somewhat more soluble, but large alkyl halides are usually very insoluble in water. So when alkyl halide thing, now alcohols are soluble in water, no? Alcohols are showing a bit of a higher solubility because the OH group is capable of producing hydrogen bonds with water. OH group can produce hydrogen. No matter where it is, it usually can produce hydrogen bonds. So therefore alcohols are somewhat more soluble in water than alkyl halides. Alkyl halides are less soluble in water compared to alcohols. Now you take alcohol that has dissolved in water, you do the reaction, and the produced alkyl halide happens to be less soluble in water. So therefore water becomes turbid, right? Like, you can't see through it that well, right? Have you ever seen water? Have you ever seen Tambili water? You have seen, obviously. There's this, like, it's not clear, right? Like, especially in certain cases, it's not very clear. There's this very opaque look to it, right? Depending on the king coconut you are referring to, right? So certain cases, if you have, like, more particles in it, it is becoming slightly unclear to you. So something like that will happen when the alkyl halides dissolve in water. So we call that turbidity. Turbidity. So since alkyl halides are not very soluble in water, as they get formed, the medium becomes turbid. Is that clear? So based on how long it takes for the medium to become turbid, we can figure out whether it is a primary alcohol, secondary alcohol, or a tertiary alcohol. Is that clear? So that's a very important reaction. We'll talk about it separately under a separate heading after this, because other reactions are self-explanatory. There's no mechanisms to be learned about these, so don't worry. Here also no mechanisms, don't worry about that as well. So we have this alcohol reacting with something called PCl3, phosphorus trichloride, PCl3, and it produces alkyl halide with, this product is also important, H3PO3, phosphorus acid, right? Not phosphoric, phosphorus. This one also produces the same product, but in this case, when we are using PBr3, we get a alkyl bromide. This is alkyl chloride. This is alkyl bromide. Is that clear? We call this a chloromethane. This is bromomethane. And instead of using these, most of the time we end up using this. This is something that you can see in many conversions. This one also is quite common in many conversions. But you need to know what the difference between these two are. When you are reacting with this, you produce our main product as well as phosphorus acid as a byproduct. Here, we don't produce H3PO3, instead we produce POCl3. This is the structure of the molecule. I thought I'll give you the structure so that you have an understanding of how it looks like. Apart from that, we form HCl gas. Usually HCl in this particular reaction, based on the reaction conditions, is produced as a gas. And that gas tends to look like a bit of a white color smoke. Right? So we don't say white smoke, we say it appears to be misty, like a bit of a misty fume, but like a mist. Is that clear? So that is another observation in this reaction. Here there's no such observation, but when it comes to use of PCl5, we see that observation. Is that clear? So out of all of the reactions, the most important one would be this, right? So in the sense there's more to be learned about that. Other than that, everything else, there's nothing to be learned additionally about that. Okay? So write a small heading, Lucas reagent, sometimes referred to as Lucas reagent. I've heard both the pronunciations, so whichever one you like you can use, Lucas or Lucas reagent. Can write zinc chloride together with concentrated HCl. Zinc chloride together with concentrated HCl. You took this down, right? Zinc chloride together with concentrated HCl is referred to as Lucas or Lucas reagent. This is used to identify primary, secondary and tertiary alcohols. You can write tertiary alcohols can easily produce an intermediary tertiary carbocation, that happens to be quite stable. Therefore they undergo reactions with Lucas reagent faster. Okay, students, so what that means is just something similar, but I can't say exactly the same situation here. But can you remember when it comes to alkyl halides, we discussed primary alkyl halide, secondary alkyl halide, tertiary alkyl halide, right? So when it comes to SN1, SN2 mechanisms we discussed, can you remember SN2 mechanism? Initially, so not SN2, SN1 mechanism, initially what happens? We have the tertiary alkyl halide directly turning into a tertiary carbocation, right? Why was this possible? Because the tertiary carbocation was quite stable. So then they remove that carbon halogen bond and turn into tertiary carbocation easily. Somewhat similar situation happens here when it comes to tertiary alcohol as well. So when the Lucas reagent is added, they can quickly turn into the intermediate product, which is the tertiary carbocation, which is somewhat more stable, and then only the Cl minus comes and attacks here and gets added here, right? But when it comes to secondary and primary alcohols, the formation of the carbocation becomes a bit more difficult for them. Why? Because the carbocation is not very stable when they form one. Is that clear? So because of that, the reactions with secondary and the primary alcohols is somewhat more delayed. It takes a long time for them to react with Lucas reagent. Is that clear? Okay, write down the next point. However, due to the primary and secondary alcohols, carbocations being relatively unstable, due to primary and secondary alcohols, carbocations being relatively unstable, formation of alkyl halides through this reaction takes a longer duration. Formation of alkyl halides take a longer duration. As a new and main point, please write. Are you joking? Okay now?
Yeah.
Right. Okay, so last point, please write. Produce alkyl halides are less soluble in water than the alcohol. Therefore, as the alkyl halide is produced, aqueous medium will become turbid. Aqueous medium will become turbid. Is that clear? So now, this is primary, secondary and tertiary. So they will convert into these alkyl halides. This one will produce CH3, CH2, Cl. This will produce CH3, CHCl. So we have Lucas reagent. So students, since they are not very soluble in water, this produces a turbidity almost immediately. Turbidity is produced almost immediately. Right? Turbidity is produced after a short period of time. We can say roughly about 5 to 10 minutes. Right? About 5 minutes maximum. Right? It doesn't take 5 minutes even. Right? This turbidity is observed after a long period of time. Usually over 10 minutes, could take 15 or so. Is that clear? So based on how fast we observe the turbidity, we can comment on whether it's a primary, secondary or a tertiary alcohol we were dealing with. Is that clear? Imagine they say you have 3 different alcohols, A, B, C. Identify whether A is a primary alcohol or a secondary alcohol, or you just have to figure out which one is a primary, secondary and tertiary. So you react all 3 of them with Lucas reagent separately. So based on how long each one takes to produce turbidity, you can comment on whether they are primary, secondary or tertiary alcohols. Is that clear? Take this down. Those of you who are done, students, so there's only 2 more types of reactions to study about alcohols. We'll do some questions about alcohols afterwards. So if there are any theory part related questions about this, ask me now, while others take it down. Any questions? Nothing? Okay. Right. Let's see. I will ask you questions afterwards. Now, take a new heading. Elimination reactions of alcohols. Elimination reactions of alcohols. Elimination reactions of alcohols. This one is easy. You quite like the whole ethanolic NaOH reaction. I've seen you remembering it a bit more than others. So here we have similar reaction, elimination reaction. So if you take elimination reaction of alcohol, what happens here is we have let's say simple alcohol like this, right? We can convert an alcohol into an alkene, right? We can convert alcohol into an alkene by adding concentrated sulfuric acid and heating it, or by adding anhydrous aluminium oxide and heating it, right? Anhydrous aluminium oxide and heating it. In either one, what actually happens is OH group will leave with a hydrogen from the adjacent carbon. Keep in mind, whenever hydrogen leaves from the nearby carbon, that carbon has to have like a lower number of hydrogen. Now imagine, now in this situation there's only one nearby carbon now. In certain other situations you have two carbons on either side. So then we choose the carbon with the lower number of hydrogens. Is that clear? In this case we don't have option, no? So the nearby carbon there's only one nearby carbon. You don't have another nearby carbon. We talk about, when I say adjacent or nearby, that means there is a carbon atom bearing the OH, we can't consider that. Other carbons near to it, meaning directly bonded to it. Is that clear? Those are referred to as adjacent carbon. So here we have only one adjacent carbon, so a hydrogen from the adjacent carbon will also leave. So they are leaving. We make them leave. So therefore we say it's an elimination reaction. Is that clear? Therefore it's an elimination reaction. We can say there's a water molecule produced here. So what you produce is a alkene. Is it understood now? Right? Take this down. Remember this. You will see this in the next conversions that I'm going to give you. Write the product here as well. Like for example, I want you to write the product that you form here. I want you to write the product here that you produce. Let's say I write anhydrous aluminium oxide, Al2O3, and I heat it. You need to definitely heat it, students. If the heating is not done, it will not happen. So I want you to write the product that you produce. If you don't heat it, nothing will happen. What is the product? Can someone tell me? Where's the double bond? Now this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. Where's the double bond? Is it between 1 and 2 or 2 and 3? 2 and 3? Very good. Yes, answer is 2 and 3. Why? 1 and 2 has, now if you, this OH won't leave with a hydrogen here. Why? This carbon has 3 hydrogens, but there's another adjacent carbon, right? That carbon has only 2 hydrogens. These 2 carbons are referred to as the adjacent carbons. Actually, these 3, right? All 3 are considered. So, out of the 3 carbons that are considered to be the adjacent carbons, this one has the lowest number of hydrogens. So, we take a hydrogen from there and form the double bond between those 2 carbons, right? So, the product would be CH3, CH, CH3 here, CH3 here, and yes, that's it, right? The oxygen, OH group leaves along with the hydrogen here. So that's the product. Okay, clear? Right. So take the next heading, oxidation reactions of alcohols. Oxidation reactions of alcohols. Can write under that, we'll take a small table. Okay, under that we'll take a small table. We'll write something down. We can write the following oxidizing agents. Following oxidizing agents can be used to oxidize alcohols. Take this down. Let me know when you're done. Right. So students, these are strong oxidizing agents, right? These guys, normally we use these two more mainly, potassium permanganate and potassium dichromate. So usually we have learned about what happens there as well. So we can use H plus CrO3 as well. That's somewhat rare that we see that in reactions, but they can be appearing in certain questions. So remember this as well as a good oxidizing agent. Obviously the strongest out of the lot will be H plus KMnO4, right? As we go down the strength of oxidation decreases, right? So this is the strongest oxidizing agent out of the lot. And then we have mild oxidizing agent like PCC. PC stands for pyridinium chlorochromate. Right, pyridinium chlorochromate. This is the formula of that. Actually, the actual structure looks like this. If you ever come across it and wonder what it looks like, okay? Chlorochromate ion looks like this. Right. So the oxygen bears the negative charge. I will write it a bit close. Oxygen bears the negative charge. Here nitrogen bears the negative charge. So we have, this is the pyridinium part, this is the chlorochromate part. Pyridinium chlorochromate. Is that clear? So we normally don't bother with all of that. We just write PCC. Now the reason we give the formula is, there are some questions, if you study past papers you would see, there are some questions, students, where they don't directly give you all the reagents needed for the reaction. They say use the reagents that are given in the box below, and in the box, like in the certain section of the paper, they have given you all the reactants you need. But instead of directly given PCC, they will give you these separately, this separately and this separately. Then you should know, okay, these things together, these two things together is what? Pyridinium chlorochromate, PCC. Is it understood? So then you know, okay, although box doesn't directly say PCC is given, you look at the formula, you know this is PCC. Is it clear? So we have now learned the different types of oxidizing agents that are there. Okay now? So with this we can now finish off the lesson after doing the next step, right? So can I erase these now? Yeah? No? It's okay, I'll give you a minute. Okay, right. So now if you take alcohols, we know there are three different types of alcohols, right? So if you take alcohols, there are three different types of alcohols. We have primary, we have secondary, and we have tertiary. Now, out of the lot, I would say primary is the one that, like, is going to have so many things to be discussed about. Right? This is a primary alcohol. This is a secondary alcohol. And this would be a tertiary alcohol. So, if you take primary alcohol and add a strong oxidizing agent, right? I don't have to write the number of different oxidizing agents here because I have given you a list. Any strong oxidizing agent can convert a primary alcohol directly into a carboxylic acid, CH3, C double bond OOH, directly to a carboxylic acid. Is that clear? There's no other two words about it. Actually, what happens is, students, a strong oxidizing agent first converts it into an aldehyde, and then aldehyde further reacts with it and will produce carboxylic acid. Is that clear? It's a two-step reaction. First the aldehyde is formed, then the aldehyde is converted into carboxylic acid. Now, if you want this to stop at the aldehyde form, imagine I want it to stop here, right? I want it to stop here. So that's an aldehyde. How do I stop it there? If you use a strong oxidizing agent, it goes there. How do I stop it here? You use a milder oxidizing agent, which is PCC. So if you use PCC, what do you get? We get the aldehyde. Is that clear? If you want the aldehyde to convert into this, we can add again a strong oxidizing agent. The aldehyde will easily convert into carboxylic acid. Is that clear? Do you understand? Right. So, yes. So when it comes to the secondary alcohol, if you add either a strong oxidizing agent or a weak one, right? So for example, I write strong oxidizing agent or a weak one like PCC, PCC, either one can convert a alcohol into what is known as a ketone. We learned this in the beginning of our organic chemistry lessons. When it comes to tertiary alcohols, strong oxidizing agents or weak ones. Now obviously, if the strong oxidizing agent can't do anything, the weak one can't definitely do anything. So even strong oxidizing agents will not have reactions with tertiary alcohols. Is that clear? Reason being, students, for an oxidation reaction to take place, carbon bearing the OH should have at least one hydrogen. So tertiary alcohols, you can see carbon bearing the OH doesn't have any hydrogens in it. Is that clear? Carbon that is connected to the OH group doesn't have any hydrogens here. So this carbon can't undergo oxidation in the presence of a oxidizing agent. This carbon has hydrogen, this one has two hydrogens, right? So either way, if the carbon bearing the OH has hydrogens only, oxidation can take place. Is it understood? Right. So take this down. as a special note, please write. When primary alcohols are oxidized, using a strong oxidizing agent, initially an aldehyde is produced. That aldehyde further reacts with the oxidizing agent. And produces a carboxylic acid. Okay, students, so now this is the reaction that takes place. You can take it down. Now one thing to keep in mind, primary alcohols whenever react with a strong oxidizing agent directly goes all the way to carboxylic acids. Can secondary alcohols produce carboxylic acids? No, they can only form ketones. Is that clear? They will not go all the way to carboxylic acids. Tertiary alcohols will not do anything. Okay. Now some additional information here, students. In this kind of reaction, what we do is we take a round bottom flask or pear shaped bottom flask. We'll just draw a round bottom flask here, and we connect it into a condenser, right? And then we have our alcohol, primary alcohol, along with the oxidizing agent here, this and this, let's say, are mixed here, and then we are heating it because you need heat for this reaction. So when they are reacting together, initially produced substance is aldehyde, right? So when you are reacting alcohol with this, you produce a aldehyde here. So now this mixture becomes a mixture of alcohol plus aldehyde. Right? So alcohols can form strong hydrogen bonds between themselves. Aldehydes can't. Right? So therefore aldehydes have a little bit of a lower boiling temperature. Slightly lower. So when you are heating them, the aldehyde will get evaporated. Right? But we have a condenser there. What happens is aldehyde goes evaporated and goes up, and then it again condenses because there is a condenser here, and then it falls right back into the reaction mixture. In the reaction mixture, what do we have? Oxidizing agent. Enough and more of it is there. Then what happens? It further undergoes oxidation to produce carboxylic acid. Is that clear? Initially the aldehyde is produced, goes up, falls back down, reacts with the excess oxidizing agent that is there, turns into the carboxylic acid. Is that understood? Is that clear? Although in our syllabus we don't really focus on this a lot, they can ask you questions like this as well, so that's why I'm trying to give you this part as well. As I told you, since the aldehyde has a little bit of a lower boiling temperature, what we can do is we can use a simple distillation setup. If you use a simple distillation setup, now don't write this as an answer, I'm preparing you for a question that might come in our syllabus, because you learn about distillation and all that also later down the line. So when you heat this mixture, along with the mixture contains alcohol and the oxidizing agent. When you heat the mixture, these two things will react and will produce this, right? If you keep heating, the produced aldehyde will evaporate and will go up. right? As soon as it is produced, it won't directly react with this. It might take some time, so it will evaporate and will go up, right? So as it goes up, if there is a Liebig condenser connected here, what happens is it will get collected through the Liebig condenser, it will get condensed and get collected to a different container. Is that clear? So we can separate the aldehyde without the use of PCC as well, but in our syllabus we don't normally talk about it. I have a feeling this could be a type of question that they can ask about, like, you know, after you learn about condensation and after you learn about different reactions revolving around what do you call it, boiling temperature based separation of liquids. Okay, so this is actually a mechanism that we use in other like, you know, if you, the A level is not the only science that you have to learn. So when it comes to studying other theory parts revolving around this, you will see if you use a simple distillation method, we can have aldehyde separated as well, but in our syllabus we don't talk about it a lot, so I'm not going to give you that theory part. I just want you to know that this could be a probable question that can be asked because it is not taught to you. So if you are asked anything about fractional distillation or simple distillation, this type of question can come. Okay, for the time being, remember, if you add H plus KMnO4, you produce the aldehyde. The aldehyde will further react to produce carboxylic acid. So most of the time, like I have given in the summary, we don't show it in two steps like this. We just show it in a single step because eventually anyway we are going to end up with the carboxylic acid. Is that understood? Right. So shall we move on to some questions? You took this equation down, right? If you didn't take the equation down, take it down. The other parts are not needed. I just wanted you to have that additional understanding a little bit. So take this equation down. Okay, now let's do a question. We'll start with a few questions. I will give you a few here. So let's start with this. You must be tired of seeing this, but this is how most of the questions would start, okay? Let's say you turn this into, this is somewhat similar to what we studied earlier. That's the first question. I will leave some space here and I'll write the second question, otherwise you can start doing this question. Attempt these two questions. The first one should be the easiest to you. Second one is somewhat easy. But I'm pretty sure you're going to find the second one the easiest. But based on the past questions we have done, first one must be the easiest for you. First one done? Oh, sorry. There you go. Okay, so now you're not like you have done something additional where you didn't have to do that. Like for example, this is perfectly the path that I want you to take, except for one step. Okay, now here when you add these two together, and another thing is this is not a covalent bond. This is a iron, we say ethoxide iron and Na. So this is not one, that's a separate one. But what I'm trying to say here is, when you add these two together, put this section. Is it seen there? Do you see this straight chain section here? No, right? There's this oxygen is in the middle carbon. Right? So you didn't have to do this. Right? You could have gone from here itself and done the other part. Yeah.
When we add sodium hydroxide directly, it get connected to this carbon.
Yes, so isn't that what we have there? Right? Like imagine when you have connected to the corner, then the product should be CH2, CH2, CH3. No, I don't have that. I have like this bent one. So here, if this is the carbon chain, 1, 2, 3, in the second carbon only the oxygen is there, no? Not on the first carbon. Anyone wants to have ask a question about the first one? Up to which parts have you done in school? These parts. Organic, did you start? Not yet. Oh, okay. I'll give you the recordings. You drop me a message. Did you called me once, right? I'm sorry. Regarding what was it? Group. Last week recording. I haven't still uploaded it. I will upload it and give you soon. Okay. I'll be uploading both of them today. First one. Oh, very good. Yes, exactly. That is correct. That is correct. Very good. Can I see? Have you gone through it? Right. So, let's see. I think the first one, second one is easy. Let's take a look at the first one. Now, students, whenever you see this, now I told you, if you see something like this, R connected to, like C triple bond carbon, another R, this kind of group came and connected to this through what? An alkyl halide. If an alkyl halide and this kind of section reacts, then you have this, right? No two words about it. That's if you have two molecules are joined together. If not, sometimes we can have the entire molecule with two BRs connected here, and then two BRs can leave to form a triple bond there. That's another one. But mostly, if a shorter molecule become a longer molecule with something like this, then it is mostly through alkyl halide reactions. And another thing is, if you see a O in the middle, like we are starting with a short molecule, and then we see O in the middle, that is also through alkyl halide reaction. You should remember alkyl halide reactions, they are quite nice. So, if you take an alkyl halide and add something called a, what do you call it? Alkoxide ion. Alkoxide ion means if you take a sodium and react it with an alcohol, sodium and alcohol react to form what? Sodium alkoxide, right? This is a sodium alkoxide, so this is an alkoxide ion. Alkoxide ion will react with the alkyl halide and they will join together, and you will have something like RO R dash. This is a ether, and ether is usually easily produced with the use of alkyl halide and alkoxide ions. Is that clear? So how do you get to this? Now imagine this alkoxide ion section. Now if I draw, what are the two main things that are used here is, you can see CH3, CH is present here, another CH3 present here. So that means the Cl group or Br group was connected to the second carbon, right? We'll connect a Br, connect to the second carbon, and here also the oxygen is connected to the second carbon. So that means we have had something like this. Bear with me. Okay, so what we have here is this alkoxide ion reacting with this to produce this. Is it understood? So this negatively charged oxygen will attack this carbon and the Br will leave, and this oxygen section along with this carbon, they will join together and will form this. So now we have to figure out a way to produce this as well as that. So producing this is super easy. You take this and directly add it with HBr. Hydrogen goes to the place where there is more hydrogen. Bromine goes to the place where there is less hydrogen. So bromine comes here. On the second carbon, bromine is there. So this thing also is the same thing as this, but on the second carbon, a bromine is there. The third carbon got the hydrogen. Is that clear? So just because it looks different, doesn't mean it's a different molecule. This is written in a straight manner. This is drawn a little bit bent. It's the same thing though, right? So I will, if you want, I will show you the initial product that is formed. CH3, CH, CH3. There will be a bromine here, right? There will be bromine there. So this is the same thing. All I have done is I have bent this and bromine is taken here, right? That's it. You should be able to see that. Okay. So and then we can get to the final product. Now I'll have to, can I do this one first, because otherwise anyway I have to erase this otherwise. Okay, I'll do this one. This is super easy. What do? We have formed a ketone starting from this. What can we do? We can add dilute H2SO4 and we can heat. What do you get then? An alcohol. You can get an alcohol. So when you do this, what happens is the water addition. Water molecules have a hydrogen and OH group. Right, that's how we see it. Hydrogen goes to the place where there's more hydrogen, OH goes to the place where there's less hydrogen. But these two carbons are identical, no? So we can't say one carbon has more hydrogen than the other, no? So we can attach it to either carbon, no problem. So I just thought I'll attach it here because they are both the same. So we have something like this. And then if you add H plus KMnO4, or even PCC is fine here because it's a ketone, right? If you add H plus KMnO4, it will anyway stop at a ketone, it won't go to carboxylic acid. If you add PCC, it will stop at ketone, right? So anyway, if you take a secondary alcohol, this is secondary alcohol, add H plus KMnO4, which we learned a little while ago, you produce a ketone. Is it understood? I will erase that in a bit. It will be easier for me to discuss the other one then. Done? Right. And then here we have this. We can convert this into a alcohol by adding aqueous sodium hydroxide. Right? Aqueous should be written within brackets. Okay, and then we will get CH3, CH, CH3, and there will be OH here. So again, this is quite similar to this. Okay, only difference is this has a Na plus. So we can easily get to that by reacting this alcohol with sodium metal. So this alcohol reacts with sodium metal. This hydrogen goes away. And this oxygen becomes oxygen becomes negative, minus, and then there will be a sodium ion attached to the negatively charged oxygen. It's an ionic bond. Sodium plus, oxygen minus. Right? That's ionic bond. That's what we have indicated there. So it's same thing. Right? This is written in a straight manner. I have taken this and we have bent it and written. I have taken this molecule and bent it and written it here. Right? It's not a different molecule. Right? You have to start seeing it. So when I added sodium, it turned into a sodium alkoxide. So this can react with the alkyl halide and produce that. Is that clear? So these alkyl halide reactions are quite important because they increase the length of carbon chain. Right? Mostly. It makes two molecules join together easily. So these are important reactions. Remember those. Okay, so this is the reaction. So you will start seeing these patterns when you do more questions. So the ones that I have done, I want you to remember. Okay? I'll give you another one of these later, but before we take a break, I'll give one more question, okay? I'll give you a break after that. Hungry? No, right? Like, why? Like you didn't have lunch before coming here? Right. I think the breaks in these classes are meant for teachers, not necessarily for students, because the teacher can't go on like teaching for too long. Because you guys, like, you know, have the opportunity to eat even during the class if you like. Not really, but what I'm saying is you can eat, right, before coming to the class. You can even have a toffee here if you like, but teachers can't do it. So anyway, so are we done with this? I will give you a simple one so that you feel a little bit happy about getting the last one right. Do this one. There aren't two molecules joining together or anything like this here. It's a simple conversion, right? Same molecule, you convert it to something else, right? See if you can get it done. Are we done? Anyone? Right. So, yes, at one point we'll have to use this. But now if you use it like this is a secondary alcohol now. Then what you would form is a ketone. Secondary alcohols in the presence of oxidizing agent will produce a ketone. Okay, shall we attempt this question? Good, I think you are on a good path. Right, now everyone, let me ask you this question. Okay, this is alcohol. That's a product that is usually produced through oxidation of an alcohol. Right, we learned about it. But oxidation of what kind of alcohol produces a carboxylic acid? This is a carboxylic acid. Oxidation of what produces this carboxylic acid? A primary alcohol. Oxidation of a primary alcohol produces a carboxylic acid, right? COOH means the same thing as this, right? If you are wondering what COOH means, right. That and COOH is the same thing. Okay, so a primary alcohol when oxidized produces this. Now you can start thinking from this corner, or if you can't connect this corner and this corner together, then let's take a look at the final product and see what would have been the one before the last. Right, these are different ways of thinking. So one before the last could have been something like this. Could have been. We don't know for sure. Could have been something like this. Right, so if you oxidize this using H+, KMnO4, you get a carboxylic acid. Right, simple, no? Now the problem is, I have been given a different alcohol to the alcohol that I need to do this conversion. So then what do we do? How do we shift this OH to this position? Is there a way to shift the OH? Yes, we can shift OHs. Is there a single reaction that can be used to shift the OH? Obviously not. Right, you have to use different conversion methods to get to that. Is that clear? There's no single reaction saying OH here, now OH is here after doing this reaction. Obviously not, we didn't learn anything like that. So what do? We can form a double bond here, right? And then we can open the double bond and get a OH here. But again, it's not as simple as I say. We first get a double bond. How do you get a double bond? Either one location is fine. How do you get a double bond here? If you have a OH, tell me. We learned about it today. What is that? You are going to tell me now. What do we add here? What do we add here? You have to tell me. We learned it today. What is it? Anhydrous, aluminium oxide and heat. What else? There's another one. Concentrated sulfuric acid. Now students, you need to remember these things. Okay. So anhydrous, aluminium oxide, Al2O3, and heat. So you form this CH3, CH. So hydrogen can leave from this nearby carbon or this nearby carbon. Either one doesn't matter because both have the same number of hydrogens. So I'm going to remove it from here. Right? If I removed it from here, it's the same product that is produced. Same thing. Right? So this is produced. Now I need this. How do you get a OH? Now I'm not going to use that reaction, I'm just asking you. How do we get a OH added across a double bond? What is the reactant? If you want now double bond is there. If you want to add a OH, like open the double bond and add OH, what do you add? Dilute sulfuric and heat. But if I add dilute sulfuric and heat here, students, again dilute sulfuric is adding a water molecule. Dilute sulfuric is adding a water molecule. So at that point, hydrogen will go to the place where there is less. Sorry, hydrogen will go to the place where there is more hydrogen. OH will go to the place where there is less hydrogen. So hydrogen will go here, OH will come here. Again the same thing as what we saw earlier. So we can't add dilute. We can't add dilute sulfuric and heat. That is not possible. Then what do? We can do HBr addition, no? So if you add HBr again, be careful. If you just add HBr, hydrogen goes here, Br goes here. We can then, Br can be changed into OH. But again useless if Br is here, no? So then what do? We can get HBr along with the peroxide. We can write hydrogen peroxide or organic peroxide. Organic peroxide can be referred to as, written as this. Right, this is organic peroxide. You can write CH3O, CH, like, you know, we can, instead of writing R, we can write this CH3. Right? So, and then you produce this CH3, CH2, CH2Br. Right, you produce this. Why? When you have a peroxide in the presence of HBr, they follow anti-Markovnikov's addition. Hydrogen goes to the place where there is less hydrogen now. Earlier, hydrogen used to go to the place where there is more hydrogen. Now, according to anti-Markovnikov's, it is going to the place where there is less hydrogen. Hydrogen goes here, bromine goes here. Understood? So, because of that, students, we produce this. And then if you add aqueous sodium hydroxide, what do you get? A primary alcohol now. Is that clear? So these are tricks, like, you know, shifting the position of OH is a simple trick. Shifting the position of double bond is a simple trick. You should be able to figure these ones out. Okay. Is that clear now? So take a small break, students. I'll meet you again at 5:40, right? So take a small break. We'll meet you again at 5:40. Right. We will start now. You have a question? Tell me.
So can you please explain that last week is part again?
Last week?
This part.
This part. Biphenyl and whole part. Vinyl chlorides and biphenyl chlorides are not stable. Okay, so there's no explanation that is given for them as such. Just the fact that having a double bond on a carbon like this, when it comes to carbon with a double bond here, having a positive charge is not very stable. And having a positive charge on benzene is normally not stable. That is just two facts you need to remember. There's no further explanation given beyond that point. It's just that having a positive charge here on this carbon like this, like there are no supporting groups here, and plus there's a double bond here. So at that point, these carbons are not going to be considered very stable, and so is this one. This is also considered to be quite unstable. Now this one, of course, we can understand why this is not very stable. I will talk about that there. So yeah, and what have you written here? What is this? You need to complete that, okay? Yeah, you need to complete this part. Okay, I will explain it to you separately after the class. Otherwise, we are going back. So if you have any questions, yeah, you can talk to me after the class. I'll help you out. Or else, if it is related to the part that we are doing right now, you can ask me now itself. Okay, so now students, we are done with alcohols. But we do have to talk a little bit about another type. Another type of molecule that is somewhat like an alcohol but isn't. OH. So we can see here to a benzene molecule, OH group is connected. Right? This is not considered to be alcohol. This is a separate category of its own. These type of molecules are referred to as what molecules? Phenol molecules. This is phenol. Now we don't call it separate alcohol. We just understand it as a separate category of its own. It's called phenol. Now alcohols and phenols are different, right? Alcohol behavior and phenol behavior is different. Now for example, if you take alcohols, we learned alcohols can react with sodium and form sodium alkoxide, right? But we learned alcohols are not reactive enough to react with sodium hydroxide, right? They can't show reaction because alcohols are not strong enough, or we say alcohols are not acidic enough to react with sodium hydroxide. Okay, and obviously alcohols can't react with sodium carbonate as well. To react with sodium carbonate, you need to be good, strong, considerably stronger type of an acid, right? So carboxylic acids are like normal referred to as weak acids, but when it comes to talking about carboxylic acids as an organic acid, out of all of the acidic compounds we learn under organic chemistry, carboxylic acid happens to be having the highest acidity. Okay, but still compared to normal mineral acids like HCl, HNO3, carboxylic acid is referred to as a weak acid, right? So anyway, alcohols can't react with any one of these. But phenol on the other hand, yes, it shows a reaction with sodium, no problem. It will form sodium phenoxide, or we say sodium phenate ion, sodium plus and phenate ion or phenoxide ion. And it can also show reactions with sodium hydroxide. Why? Because phenol is slightly more acidic than alcohols. Phenols are more acidic than alcohols. So therefore students, they are capable of reacting with sodium hydroxide as well, and we are producing the same thing, right? You produce sodium phenoxide, but again, phenols are not reacting enough to react with sodium carbonate. They can't react with sodium carbonate, no reaction there. Is that clear? So these two are definitely two different things, and we are going to learn about that next. This is just an example to say, I just give you this example to say that phenols are slightly different to alcohols, right? They also have OH group connected to benzene, but alcohols and phenols are slightly different to one another. Write a new heading, phenols. Right? Phenol is an aromatic compound where a benzene ring is connected to a OH group. Take this down. Right? The next point, after taking this down, next point, phenols are more acidic than alcohols. This is because the phenoxide ion produced is more stabilized through resonance structures compared to phenol. To the same point, right? Phenol has a positive charge on a very electronegative element, oxygen, whereas phenoxide doesn't. I want you to take this down. You should be able to draw it without looking at the board. These are resonance structures. You should be able to draw it without looking at the board. So what happens is the electron pair travels. Now the lone pair on oxygen gets between the oxygen and carbon here. So when there's a double bond formed here, this carbon can't have 5 bonds, so therefore one bond turns into an electron pair, right, on the other carbon. So then that is the first resonance structure. So then the electron pair again comes back into the second position here as a double bond, and then this carbon over here, it has 4 bonds already, so it has to break one bond to accommodate the new bond that is forming. So therefore this bond breaks, electrons are given here, right? So that continues to happen. So the negatively charged lone pair keeps on shifting between different places. And also, while you take this down, observe where in the resonance structures where the negative charged or where the lone pair is going to be present. I can't say negatively charged lone pair. A lone pair comes, at that point the carbon will exceed its electron number, forming a negative charge there. But observe where the electron pair is going. It's here once, and then this is the ortho position, para position, again ortho position. In ortho and para position, the negative charge is going to be present in most of the resonance structures. Something to keep in mind. Done? Your question, Prasadi? What is it? You confused somewhere? Yes? Tell me. The negative charge. So now we see a OH bond. No? So if hydrogen leaves, now when it comes to acid, H plus leaves, right? So then the bond electrons goes to oxygen. So now, for example, now if you have a question like that, please ask. So for example, if you have something like this, this is the basic OH bond. If hydrogen leaves as H plus, the bond electrons come here. So now oxygen has altogether what? 1 electron here in this bond, and then there are 6 electrons around oxygen. Oxygen can have only what? 6 electrons of its own. So 1 electron here and 6 here, altogether 7. So therefore oxygen is negative charged. Okay, so I have to give you a note under this. So write a new subheading under these things that can be explained, using the resonance structures seen above. First point. First point under that. So these first points are like subheadings, okay? Write down cleavage of OH bond. Cleavage of OH bond. Right? OH bond cleavage can happen easily. As the phenoxide ion is more stabilized compared to phenol, right? Therefore, phenols become more acidic than alcohols. So the acidity of phenols is higher due to this reason. Therefore, phenols become more acidic than alcohols. Now let me explain this to you, students. If you take this, we know these kind of molecules with double bonds usually have resonance structures. They can have this double bond switching up and having resonance structures. And we know earlier also when we started talking about benzene, we learned about the fact that the lone pairs of these kind of groups, when we talked about the fact that OH is a orthopolar directing group and ring activator, we learned these lone pairs get mixed with the benzene ring through this double bond formation here, right? So now when you analyze these resonance structures, especially these three structures, you can see oxygen is bearing a positive charge, which is not very stable for oxygen. Oxygen is the second most electronegative element in the entire periodic table. Having a positive charge on oxygen is not very stable. However, in the phenoxide ion, we don't see that. In all of these resonance structures, you never see a positive charge on oxygen. Instead, we have negative charges on two of them, and all the others will not have a positive charge on oxygen. Is that clear? Which makes these more stable than these. So we say phenoxide ion is more stabilized through resonance compared to phenol. Phenoxide ion is more stabilized through resonance than phenol. Is that clear? So when given the opportunity, phenol will release the H plus and become phenoxide. Is that clear? Because phenoxide ion is slightly more stable compared to phenol. Is it understood? Right. So then under that you can write these two reactions. You can write due to this, you can write as a new point, due to this phenol show reaction with both sodium and sodium hydroxide. Take this down. Before you take this down, you can write after that. However, phenol is not acidic enough to react with sodium carbonate. Phenol is not acidic enough to react with sodium carbonate. Is this okay now? Done? Now I hope you will start writing a bit faster. We have to. Okay, right? So now, then write the second point. Now the first subheading is done. First subheading is done. Second subheading, like write 2, right? 2. Cleavage of carbon oxygen bond. Cleavage of CO bond. CO bond. Cleavage of CO bond. Under that, right? Phenols do not show nucleophilic substitution reactions. Phenols do not show nucleophilic substitution reactions. That are seen in alcohols. Nucleophilic substitution reactions that are seen in alcohols. This is because unlike in alcohols, the carbon oxygen bond in phenols show a double bond nature as seen in the resonance structures above. Therefore, CO bond cleaving reactions will not take place in phenols. Therefore, CO bond cleaving reactions will not take place in phenol. Therefore, CO bond cleaving reactions will not take place in phenol. Is it understood? Now students, for example, we learned if you take ROH and add something like PCl3, right, PCl3, what happens? You will form RCl. So therefore this carbon oxygen bond breaks, right? Carbon oxygen bond breaks here if you take a normal alcohol. But if you add PCl3 here, nothing will happen because the carbon oxygen bond can't break here, because if you take a look at the resonance structures, the carbon oxygen bond has somewhat of a double bond nature, right? They have a double bond nature. Is that clear? And apart from that, this is another reason, each carbon here is sp2 hybridized. In alcohols, each carbon has 4 bonds. So therefore each carbon in alcohol is sp3 hybridized, right? So sp3 hybridized orbitals are longer and the bond happens to be longer between carbon and oxygen at that point, which is easy to break. But here we have a double bond nature. Apart from that, sp2 hybridized orbitals are there. sp2 hybridized orbitals are a bit shorter and the bond is anyway going to end up being a bit stronger due to both of those factors, sp2 hybridized carbons as well as the presence of a double bond. Is that clear? Understood? Right. You can write apart from that as a second point. Apart from that, in phenol, Carbons have sp2 hybridized orbitals. Compared to sp3 hybridized orbitals in alcohols. This makes the CO bonds in phenols stronger. So you can write reactions like these don't take place. Right? The last one, there's another point, third point. Take the third point, students. Reactivity of benzene ring in phenols. Reactivity of benzene ring in phenols. You can write, as seen in the resonance structures of phenol above, or as seen in the resonance structures of phenol, a lone pair of oxygen gets delocalized into benzene's cyclic electron cloud. And increases the electron density of the benzene ring. Within brackets write ring activation. Within brackets write ring activation. Okay? Then write, due to this, phenols show faster reaction rates compared to benzene. And only milder reaction conditions are needed. Compared to benzene. Examples. Examples. 1. If you take phenol and react it with bromine, right? It is so activated, students, at room temperature. Now can you remember when it comes to benzene, how we added a bromine to benzene? Can you remember? What did we use? You should remember. What did we use to add bromine to benzene? Like to form bromobenzene. What did we add? Only one bromine got attached to benzene. What did we add? To benzene, what did we add? Br2 and FeBr3, right? FeBr3 and Br2 were added together. Is that clear? So then only, and plus we had to increase the temperature also a little bit. Then only this happened. But here we are adding Br2. Actually bromine water is even fine, not just Br2 in CCl4 anything like that. Even bromine water is fine here. Bromine water is like a bromine dissolved in water, right? So that's a lower concentration of bromine. Even bromine water will react with phenol and produce not just like we expect something like this to be formed, right? We expect something like this to be formed. Bromine, only one bromine to be added, no? That's what we expect. But in reality it forms a product where 3 bromines are connected. 3 bromines are connected to phenol, right? Why? Do you see? These ortho para positions are going to be high in electron density. Do you see? Ortho position, para position and another ortho position is getting increased in their electron density according to resonance. Why? When phenol is there, oxygen has one of its lone pairs delocalized into the benzene ring, produces this. Is it understood? So because of that, students, we have this product formed, and this product is a precipitate. This is a, we call this now carbon number, we start numbering here 1, 2, 3, 4, 5, 6, right? No need to write them down, but you can see on the 2nd, 4th and the 6th position there are bromines, right? I don't want you to be like, writing them down. So we start numbering with phenol or oxygen. Sorry, this carbon connected to oxygen. So then we form what is known as 2, 4, 6 tribromophenol, which is a white precipitate. It's a white color precipitate. So one example why this is a very clear indication that phenol is easily reacting compared to benzene. Even Br2 water, bromine water can react with phenol. Benzene cannot. Benzene needs so many things. It needs bromine and what else? Bromine liquid and what else? FeBr3, a catalyst, or we say halogen carrier, right? It's a catalyst, acting as a catalyst. It needs those two. Apart from that, a little bit of a higher temperature is also needed, right? Like you guys. So what, like I have to tell you, remember this, study this. I have say behind you what happened last week. Can you remember it? Like after saying that, do a couple of questions, and then again identical question is given, and then ask you, do you get this? Still sometimes no. But there are again, like there are some students who have gone through this cycle once and then realize I have to do my own work, and then if I ask them a question, they will know the answer, and plus they will ask me questions, right? I don't see that here. So I'm just joking, but you need to be a bit more up to date with what we have done before, okay? So I expect that from you. When I ask a question from a previous part, you should be able to answer, especially organic chemistry. Anyway, so when it comes to phenol is definitely more reactive than benzene. It produces products faster than benzene, and you can see it requires only milder conditions, quickly forms tri-substituted bromine product, right? 2,4,6 tribromophenol. So take this down as example number 1. That's another example. Take this one down. Okay. Now the second reaction is, I will erase this one. The second reaction is this. We know the nitration reaction. Can you first of all tell me the nitration of benzene requires what conditions? What are the reagents and the conditions? You should remember. Nitration of benzene, one of the first reactions we learned under benzene. What do we need? Concentrated nitric acid and concentrated sulfuric, correct? Right? Very good. So apart from that, what is the temperature? 50 degrees Celsius, above 50. Okay. But when it comes to phenol, you don't need anything else. You only need nitric acid along with a temperature like 20 degrees Celsius. Even 20, that means colder temperature than this, right? This is about 25, I would say, right? Although it says 16. So colder temperature than this is required. So what happens is, students, if you take phenol, if you react it with concentrated nitric acid, right? Even dilute would do, but we write HNO3. It will produce nitrobenzene, right? It will produce nitrobenzene. Only one nitro group will add here, not like the previous one, okay? It will be producing this, or actually it can produce both of these, because the nitro group can, I will write the phenol the usual Kekulé structure way, because in our syllabus we use that a lot. So you can have OH here, or so nitro group in the ortho position or the para position, because ortho position is also electron dense here, para positions are also electron dense here. So nitro groups can attach to either position. Actually, when the reaction mechanism happens, they get produced somewhat evenly, right? So about 2 to 1 ratio. You don't need to know about the ratios, but both of them are getting produced. Both of them are possible. Is that clear? So take this down. That's the second example. Actually, instead of writing conc, to make the point, we'll write dil. I told you even dilute ones are used. So dilute nitric is enough. But in the previous one, we needed concentrated nitric along with concentrated sulfuric. None of that is needed. The temperature here is about 20 degrees Celsius. The previous one was 50 degrees Celsius when it comes to benzene. And you need a sulfuric acid molecule concentrated sulfuric acid as well. Okay, right. So now if you are done with this, those are the main few points that you need to keep in mind. That's about it. Okay, as a singled out new point, nothing related to this, but this is just a single point. You need to remember this. You can write it under a star point. Write down, unlike benzene, phenol cannot show reactions through Friedel-Crafts mechanisms. Friedel-Crafts mechanisms. Now, what does that mean? Can you remember Friedel-Crafts mechanisms? You remember? right? What was it that we used? What are the two mechanisms? Friedel-Crafts, alkylation and acylation. In both of them we use something, like, you know, the alkyl halides with something. What is the other thing that we reacted with? Alkyl halides and a catalyst was used. What is a catalyst? Anhydrous aluminium chloride, AlCl3, right? And then acylation also, AlCl3 was there. It's a halogen carrier, right? You need to remember these. The thing is, these halogen carriers, AlCl3, now aluminium has, what do you call it, only 3 bonds here, no? Right? Aluminium's octet is not complete, right? Aluminium's octet is not complete. Only 2, 4, 6 is there. Octet is not complete. Actually, aluminium atom, if you take a look into their like, you know, electron configuration and the box orbital diagrams, you realize there's going to be one empty orbital. You shouldn't be drawing it like this. I'm just trying to show you something here. It contains a empty orbital here that can, like, allow aluminium to accept a lone pair of electrons. That's exactly why it's a good halogen carrier, right? Because it takes, now for example, can you remember we spoke about like, you know, CH3Cl, right? The Cl breaks these bonds and 2 electrons are given to aluminium, and so the new bond will be formed here, right? But the problem with aluminium chloride when reacting with phenols is the same thing that I just mentioned earlier. It has an empty orbital. So therefore, it can form complexes with phenol. Instead of doing the main reaction, there's a lone, actually there are 2 lone pairs, but 1 lone pair gets mixed with this now. So definitely there's 1 lone pair on oxygen. That lone pair can get mixed with aluminium chloride and will form complexes. Aluminium chloride and phenol complexes can be formed. So due to this, Friedel-Crafts acylation, Friedel-Crafts alkylation reactions are not very possible. Is that clear? So write the reason under that. This is because AlCl3 can form complexes with phenol and interfere with the Friedel-Crafts mechanism. Is that understood? So if you have AlCl3, or apart from that, students, any halogen carrier can form complexes with this, okay, like AlCl3. Write down catalysts such as AlCl3, AlBr3, FeBr3, FeCl3. FeBr3, FeCl3 can form complexes with phenol, Therefore, they cannot be used as catalysts in reactions with phenol. Therefore, they cannot be used as catalysts in reactions with phenol. Okay, is that clear now? We are done with phenols. Right? So under phenols, the most important reactions, remember, I have given you. You need to remember those, right? So phenol nitration, phenol bromination, you need to remember, right? So normally benzene bromination uses FeBr3. Do we have to add FeBr3 to phenol? No, phenol is super activated, so it doesn't need a catalyst. it will react with even bromine water, right? Not liquid bromine. Bromine water is also enough. Is that clear? It will quickly react with phenol and produce not just normal, what do you call it, just a single substitute product. It will form 2,4,6-tribromophenol, which is a white color precipitate in aqueous medium. Is that clear? So these are things you should remember as we move along. So we are done with phenols. Since we have the time, I will get an introduction to aldehydes and we'll finish with a question. Okay, but I can't give you aldehyde based question. I don't think we can cover that much ground. So we will step into aldehydes and ketones, and I will in 10 minutes finish that and I'll give you a question, right? We finish at 7, right? Right. So take a brand new heading, carbonyl compounds. Carbonyl compounds. Carbonyl compounds. Students, any organic compound that has carbon-oxygen double bond like this is referred to as a carbonyl compound. But don't get confused. Carboxylic acid also has this, but apart from that it also has a OH group. So therefore this is not a carbonyl compound. Carbonyl compounds has only this as the functional group, right? Not any other group. So here carboxylic acids have this as well as something else, right? So when you have other things also, it is not considered to be a carbonyl group. This is a special separate group called carboxylic acid. If you only have this section, it is a carbonyl functional group. Is that clear? If you have other things like COO or else something like this, right? This is a ester, this is a carboxylic acid. Or else if you have something like this, acyl chloride, right? These are all different. The functional group is this. Here the functional group is this. Here the functional group is this. So those functional groups are different to this one. Okay, don't get confused. Don't consider this, this part is there, no, so no, this is not that, this is a different one. Okay. So under carbonyl compounds, there are two different types of carbonyl compounds. As we know, one is aldehyde, the other one is ketone. Aldehyde and ketone. So the aldehyde is this. In aldehyde, students, one of the key features is this carbonyl group, and this particular carbon is referred to as the carbonyl carbon. This entire group is known as a carbonyl functional group. This carbon is carbonyl carbon. So in the aldehyde molecules, the carbonyl carbon has one hydrogen connected to it. Is that clear? But when it comes to ketones, on both sides some sort of a alkyl group is connected, no hydrogens directly bonded to carbonyl carbon. Is that clear? But aldehydes, at least one hydrogen is directly bonded to the carbonyl carbon. Is that clear? Understood? But of course, the first member of the aldehyde family, which is methanaldehyde, or methanal actually, also referred to as formaldehyde. This is the simplest member of the aldehyde family. That one only has two hydrogens connected to the carbonyl carbon. That's the only one. From there onwards, the second member onwards, you don't see that anymore. Second member onwards, do we see that? No, we don't see that anymore. Is that clear? Right. So when it comes to ketones, ketone family, the simplest member is this. Nothing special about it, just the fact that ketones start with having 3 carbons. There are no simpler ketones than that. Simplest ketone has 3 carbons. Right? Why? Because the carbon-oxygen double bond should be in the middle. Right? So on both sides there should be alkyl groups connected to it. Right? So the simplest member is this. So the other members would be something like this. Okay. So under aldehydes and ketones, you can start taking this down, right? The new heading I gave you was carbonyl compounds, right? Under that, please take it down. You done? Right. I will remind you a little bit about naming and then I'll stop there. Right? We'll remind ourselves about naming these aldehyde and ketones. So aldehydes end with the suffix al. Ketones end with the suffix one. Ketones end with the suffix one. Bear with me. So this one has one carbon, so the code meth is used, and carbons, between carbon atoms there are only single bonds. Actually there is no other carbon here. So if there are only single bonds between carbon atoms, we always use the AN part, right? AN section, methane. So the carbon chain rated naming is up to this point, methane. And the suffix of this is Al. So suffix is Al. So this is methanol. This one is, there are 3 carbons. So this is called prop N. AN is there to show that there are carbon-carbon single bonds only. And then ketone is having the suffix ONE. So this is called propanone. Propanone. Now students, one thing with aldehydes and ketones is, when it comes to aldehydes, the carbon with the double bonded oxygen or carbonyl carbon should always be present in a corner, right? Corner position, not in the middle of the carbon chain, right? Why? Because if it is in the middle, then both sides there will be alkyl group, so it will be a ketone. If it is aldehyde, the carbon should be on a corner. So when it comes to naming aldehydes, we always start with giving that carbon number 1 because priority is given to functional group. No? So that will be 1, and then after that it will be named according. So therefore, there is no need for molecules like, let's say, something like this. If I give you something like the CH3, CH2, CH2, and the aldehyde section. There's no need for me to mention it is in the first position. I don't have to say butane 1L. Is that clear? I don't have to say that because aldehyde always it's in a corner carbon. So it will be just, the name would be what? Butanal. No need to say butane 1L. But I can't say the same about ketones. But only 2 ketones we can avoid writing the position. For example, if you take this ketone, also we can avoid its location. We don't have to say the location. For example, here, do I have to say propan 2-on? I can write it like that, it will not be incorrect, but where else could it be? The carbon, where else could it be? Can it be here? If it is there, it will be aldehyde. Can it be here? Same story, aldehyde. Right. Now this one, if the carbon is present here, we can call it, what do you call it? Butane 2-on. Butane 2-on. But what if it is present here? What will be the name? Same name, butane 2-on. So when it comes to butanone also, we don't necessarily need to write you can write it if you like. If you are feeling like, this is too much to remember, write it, no problem. But we don't need to, because butanone means just one compound. But from there onwards, you will definitely need to write the locant. Locant means the position of the double bond, the position of the carbon-carbon. So for example, this is a ketone. But this ketone can have the carbon-carbon right in the central carbon atom, like in the 3rd position, or it could be in the 2nd position, right? So having the 2nd position will be a different name to having it in the 3rd position. Is that clear? So this one is a pentane 3-on. What is this one? If you have it here, pentane 2-on, 2 different molecules. Is it understood? So therefore, you write it like this. This is pentane dash 2, actually in this case 3, not 2, 3-on. Or else you can also write 3-pentanone. You can bring the 3 to the front. Is that clear? I'm just giving you some names. Here also we'll write one more. CH3, CH2, 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 C. What is this? Pentanal. No need to say 1-pentanal, because if there is a case, all the aldehydes will be 1-1-1-1. Right? There will never be 2 pentanals or anything like that. Is that clear? So it will be absurd to always write 1-1-1 everywhere. Right? So this is the naming, how it works. I would it will be better if you can take this down. Until then, I will write a question on the other side. Students, keep in mind, our conversions get better and better the more you know, right? So next week the aldehyde section will be there. You can do much nicer conversions then. So come prepared with the previous knowledge. If you don't have that, it will be a bit of a bitter experience for you.
Do those three. I didn't space it really well actually. Right, but you can do them. Last one is a good one, so it'll, if you do it fast, I don't have to keep you after 7 a lot. First two is easy. So do you like this size or something that is smaller, like a pocket calendar size? Smaller? Y'all use that, no? Once in a while you use it. Sorry? Yeah, it's aldehyde. You're asking whether this part is one group? Yeah. It's called a aldehyde functional group. Not too long ago we learned about aldehydes. Not right now, before the break. Was it before the break? I can't remember. Before the break, yes. If you are done with any of those, at least one of them, let me know. Is there anyone who has done at least one of them? Yeah, very good.
Good, yes. You're getting there. It's okay, you haven't gone through this part, so you have to go through the theory first. First, you have done one, no? Okay, that's the easy one. Easy in the sense, a lot of students don't see it though. Second one is just one step. Right, students, now we are running out of time, so I will quickly do this. First one is an aldehyde formation. So we have a double bond here. We can't just convert a double bond into aldehyde. We need to have a OH group, right? So we can have a, what do you call it? Actually, first one I saw some of you have made the ketone correctly, but not this one. I'm sorry, I might have incorrectly said. Some of you have done it correctly. I'm sorry, because this is aldehyde, not a ketone. So aldehyde, if you had just dilute sulfuric acid here, the hydrogen will go here and the OH will come here. So therefore, it will be having OH here. So when you have OH here, it will be a secondary alcohol. Secondary alcohols, if you oxidize them, will turn into ketones, not the aldehyde. So first things first, you add HBr with peroxide. Right? We can say something like any peroxide would do. We write organic peroxide like this. Right? So then what happens is you form CH3, CH, CH2. But the difference is, in this case, hydrogen won't go to the place where there's more hydrogen. Instead, it follows the opposite. So anti-Markovnikov. That's why we use this. So when you write it, it will be CH3, CH2, CH2Br. Br will come here. So then if you add something like sodium hydroxide in aqueous medium, sodium hydroxide, Br will turn into a OH group. CH3, CH2, CH2, OH. Right? So primary alcohol now. Primary alcohol, if you had a good oxidizing agent, like strong one, it will turn into carboxylic acid. We don't want carboxylic acid here. We want a aldehyde. So what do you get then? What do you add then? PCC, pyridinium chlorochromate. PCC, correct. Is that understood? So this is how you do the conversion. Okay. The next one is, I don't think anyone had any trouble with it, or I don't expect anyone to have any trouble with it, but some of you forgot this equation. Today we did it in the beginning of the class. If you have a triple bond, how can you get it to become a ketone? What? Simple water addition in the presence of mercuric ion. Or we can write Hg2 plus and H plus H2O. Right, sulfuric acid or dilute sulfuric acid is enough. So if you had Hg2 plus in the presence of, if you had H plus H2O in the presence of Hg2 plus, it will directly into that. One step, single step, nothing more. See, you need to remember. So now we have the same starting compound, but we are now expecting to see aldehyde. Now how would you get that? How can we get that? Same starting material as the previous one. You don't have a single step to do this one. We have to do it in a few steps. Now to get an aldehyde, students, we need to have a what? We need to have a primary alcohol. Right? Primary alcohol can easily be converted into aldehyde. Through what? Addition of PCC, pyridinium chlorochromate. Is that clear? So how can we get here? Is there a method? Yes, there is a method. Right? We can add something like HBr, and then HBr can be added with peroxide to get the whole different scenario, and after that we can have
sodium hydroxide added and get there. But to do all of that, we need to have a double bond here, not a triple bond. We have a double bond. We have to have a double bond. We have a triple bond here, so what do? How do we convert triple bond into a double bond? Yes, good. Right, some of you remember. We can add palladium coated barium sulfate with quinoline. This is the catalyst. Apart from that, you need to have hydrogen gas also added, right? Because hydrogen is the one that is getting added here. So at that point, out of the triple bonds, only one bond will get hydrogenated and we will have a double bond remaining here. CH2. We form this. Then the rest is the same thing as this, right? So we have to add HBr in the presence of a peroxide, right? In the presence of a peroxide, and then what will happen is anti-Markovnikov's addition, right? So we'll have CH2 here, CH2, Br, and then Br can be added with aqueous medium NaOH, and we are producing primary alcohol, and the primary alcohol can be added with PCC, which produces the aldehyde. Okay. I would say when you go home, don't do anything else. Don't do anything else. Look at the conversions at least that we did today. Now if today is too late for you when you go home, then next day morning look at only the conversions we did today. Don't look at the answer. If you can keep a piece of paper when you are starting, okay, you take it down, you see the conversion. Try to do the conversion on a separate piece of paper without looking at the answer. Until you get the answers right, keep doing this. Is that clear? At least then what we have done will go into your minds and will stay there, right? So you will know how these type of conversions are done. These are just question type students. So the more familiar you are with different types of conversions, how do we convert a triple bond to a double bond? How do we convert triple bond to aldehyde? How do you convert triple bond to a ketone? Right? Those kind of things should be there in your memory reserves. It should be there, right? So build a memory bank that will not fail you. So with that, I'll stop the class here. I will send you. I have a document that is in Sinhala though, but I don't think you can understand. There's nobody here that can't understand Sinhala. There's a conversion list that I haven't still converted to English. So I will send it to you and try to see if you know how to do the conversions that are there. Right? I'll try because there's about 300 conversions. I don't think I can write everything in Sinhala, right? So English, right? It's difficult. It's time-consuming process. I will discuss some questions in class and I'll explain to you. If you don't understand Sinhala, I will explain to you what it means. Okay? But that's just on your leisure times do those. But I'll be continuing class here, don't worry. Right? So next week, do you have any commitments to start the class in the morning? Now your commitments are done, all done. Right? Discussion is also all right. You didn't go today? Oh, okay. Anyway, I will inform you, right? I will inform you midweek. On Thursday, I will inform you. Okay? So that will be all for today then, everyone. I'll see you again next week. And the time that we meet next week, I will inform you on a Thursday. If I don't inform you on Thursday, someone please remind me, right? So I'll see you all on Monday, okay? See you guys. recordings
Did
are?
it last week.
Oh.
And the previous week was like half.
Yes, the previous week there was a bit of an issue. I told, but that I can't help. I don't have anything to cover that up. Last week's recording I haven't still uploaded. I will upload it together today. A bit of a busy week last week, so I couldn't upload. I will upload it today. Right? Yes. Right. You can send me a message to my. You have my number. Yeah. Bear with me. You can come with me here. I'll give you the number. So, drop me a message and I will add you to the WhatsApp group. Okay, so there we will communicate everything. So, drop me a message to 077 858 7755. Yes. That's the correct number. Yes, that's the correct number. So you send me a message. I will send you the recordings that we have of organic lessons that we have done so far, because I think you have missed. You haven't done any organic at school?
Previous class I did organics, but conversions are a bit
Difficult. So